Okay, so welcome back to the lecture series of finite volume, and where we will continue our discussion where we left in the last lecture. Now, what happens to the transient diffusion case? Now, that is the case where we have a convection case. Now, we look at transient diffusion problem. So, transient diffusion problem, for these purposes again you consider that one dimensional tensile. So, C E W, this is small e small w delta x c, and if the cell height is there, that would delta y c. So, it is a uniform, again it is a uniform tensile. So, once you consider that uniform tensile, now the discretized equation for the transient diffusion term is going to be AC, and these are the coefficients in there. So, the AC at present time level is given by gamma E delta y c by delta x c plus gamma w delta y c by. Similarly, at the previous time level, this is minus rho c t minus delta c b c by delta t, which is minus rho c t minus delta t del x c del y c divided by del t. So, the CFL criteria says AC at t plus AC at t minus delta t, they less than 0, which will get you gamma E delta y c by del x c plus gamma w del y c by del x w minus rho c t minus delta t del x c del y c by del t less than 0. So, which will give you an criteria where delta t is less than rho c t minus delta c x c gamma E by del x c plus gamma w by del x w. So, in case you have, as we assume the uniform grid, and let us say gamma E is same, which is gamma, then this delta t becomes rho c delta x c square divided by 2 gamma c. So, that is the restriction you get transient diffusion problem. So, the CFL criteria for diffusion problem is gamma c delta c by rho c delta x c square, and it has to be less than half for stability. So, you see individually when you look at the convection problem and the diffusion problem, the stability limits are different, and when we combine them, so the complete unsteady convection diffusion system, so that is the one which you would like to take up next. So, transient convection diffusion problem. So, now how one can go about it? Let us consider this stencil, which is in essentially unstructured grid. So, when we are in the unstructured grid, then we have a cell connected with neighboring elements which are faces like this, and they are connecting with the. Now, here this is a transient convection diffusion problem or case, where your coefficients at the from the matrix, these are minus rho c Vc by delta t. Ac at current instance is f Nb over c gamma f Ef by dCf plus m dot f 0. Now, once we substitute this for the stability criteria, which is essentially the criteria of Act plus Act minus delta t less than 0, we get summation over f NBC gamma f Ef by dCf plus m dot f 0 minus rho c t minus delta t Bc by delta t less than 0. So, which leads to the following condition, that delta t must be rho c t minus delta t Vc divided by summation f NBC gamma f Ef dCf plus m dot f 0. So, that is the criteria one can get for both convection diffusion system. Now, this equation, the general requirement for the stability of explicit scheme. Now, the condition obtained earlier for pure convection or diffusion is in one dimensional system, and those could be the special case of this multidimensional problem. Now, again for the case of one dimensional diffusion with uniform grid, from here let us say from here one can derive those one dimensional case with uniform grid of delta x, density is constant rho, uniform diffusion coefficients gamma, then one reduces this criteria for the diffusion case, unsteady diffusion case, that delta t less than equals to rho c, which is t minus delta t, this delta x delta yc divided by summation of f NBC, which is now one can write this is gamma f, which will be now Ef by dCf plus m dot f 0. Now, this guy is 0, this guy is essentially lead to delta yc by delta xc, and gamma f is gamma E by gamma W. Now, so if the flow moves from left to right, this delta t criteria becomes del xc by uc, that is for convection. So, one case you can find out pure diffusion, other case you can find out pure convection. So, the stability constant, which is quite stringent and very restrictive, as it forces the use of extremely small cell size and the grid size in the explicit transient formulation. So, when we look at the implicit transient formulation in the later half of the lecture, we can see that restrictions actually gets relaxed quite a bit. Now, in system with backward Euler. Backward Euler is sort of a implicit scheme. Now, again what we can write, our any variable t minus delta t is written as t minus del t plus del 2 phi by del t 2 delta t square by factorial 2 and so on. So, we can find out the first derivative of this like phi t minus delta t divided by delta t, which is essentially del 2 phi by del t 2 delta t by 2. Now, this one can replace in the discretized equations, and that it will be like at t minus rho c t minus delta t by delta t v c plus L phi c at t equals to 0. Now, once we invoke these algebraic relations of the spatial operator, and then complete algebraic transient equation would be this is AC and then AC at the present location, I mean present time step plus phi c. So, this one can define this dot which will represent the transient term at the current time legend. So, this is the current time level transient term. Since we are using same coefficients AC for the space and the time, we will just make it separate like that. So, in BC AF phi f BC t minus delta t phi c t minus delta t, where the coefficients for the transient term is rho c t BC divided by delta t and AC t minus delta t is minus rho c t minus delta t BC by del t term. So, that is how we can actually get, and you can use the field operator to get the new. Now, here the time level t and the time level t minus delta t are also of opposite sign, which guarantees that phi c is bounded by its spatial neighbors at the current time step t and c is temporal neighbors from the previous time step t minus delta t. So, this implies the scheme is stable independent of the time step used. So, this is what the advantage of backward Euler, it is independent of delta t, it is a stable scheme. So, that is the important message. Now, one can actually, I mean, this is not an ideal scheme, as it is also low order, and solution obtained with the schemes are of the lower order of accuracy, unless very small time step, that is like delta t, is used. So, which is also a very restrictive condition, because then your calculation would be marching at a slower pace compared to, if you adapt to a large time step for computational efficiency, result would be very erroneous. So, there could be one more scheme which can be discussed, which is called Crank-Nicolson scheme. So, the Crank-Nicolson scheme. Crank-Nicolson scheme, what it uses the information of t plus delta t, uses the information of t minus delta t, and also at the level of t. So, it uses all this information. Now, using Taylor series expansion, one can write del phi by del t is phi t plus delta t minus phi t minus delta t divided by 2 delta t. This would be second order accurates. Now, since the order of accuracy, and now if it substitute in the equation, this will give you rho b c t plus delta t minus rho c v c t minus delta t divided by 2 delta t b c plus L phi c equals to 0. Then once we invoke the special operator, so we can write that complete system like AC phi c BC minus AC t phi c t minus delta t plus f AF t phi f t minus delta t AC t minus 2 delta t phi c t minus 2 delta t. So, it uses the information at the current time level, previous time level, and one level earlier, where AC this is rho c by 2 delta t, AC t minus 2 delta t is rho c t minus 2 delta t b divided by 2 delta t. So, this scheme what it uses that at the t plus rho phi at t plus delta t, which can be performed using the old values. However, the old values are read from the 2 levels before this one, and accordingly it will modify the system. Now, one more thing which is required, that analysis of the stability of this particular scheme, Crank-Nicolson scheme. So, this can be performed after slightly modifying the equation. In that case, what modification is done is that we say phi at t minus delta t is approximated as phi t plus phi t minus 2 delta t divided by 2. Then the complete algebraic equation, this one brings down to AC phi c 0.5 ACT phi ct plus summation of f NBC AF phi f all at the teeth level equals to BCT minus 0.5, where we write AC T plus 2 AC T minus 2 delta T phi C T minus 2 delta T plus NBC AF T phi f T minus 2 delta T. So, that is how you can get, and the which becomes AC T plus 2 AC T minus 2 delta T less than equals to 0. Again, if you go back to one dimensional system, then this equation provides you the criteria that delta T less than equals to 2 rho C T minus 2 delta T V C by m dot E T minus delta T, which is 2 rho C T minus delta T del x c del y c divided by rho C T minus delta T U C T minus delta C delta y c, which is nothing but 2 delta x c by magnitude of T minus delta T. So, which has been assumed that the advection term is discretized using the Apunt scheme. Now, using the CFL number for the convection defined by this expression, the criteria for the convection would be less than 2. So, larger the CFL limitation is very much helpful in the computing point of view, but the improved accuracy is just more important as it allows for accurate solution, which can be achieved without the need to resort to very small time step. So, especially that the second order derivative is now estimated from the error. So, now we can see the accuracy issues now. Now, implementation, if you look at these details, so the implementation details, because end of the day one has to think about from the programming point of view. Now, what happens at the forward Euler, where you get your rho C phi C at t minus rho C phi C t minus delta t by delta t V C equals to minus L phi C t. Now, backward Euler, you get rho C phi C t plus delta t minus rho C phi C t divided by delta t V C minus L phi C at t. Now, if you add these two, forward plus backward Euler, what it does, it actually add this term, and now if you add this term, which will get you rho C phi C t plus delta t, this guy gets cancelled, minus rho C phi C t minus delta t by 2 delta t into V C plus L phi C t equals to 0, which is essentially Crank-Nicolson scheme. So, this points to a simple implementation of the Crank-Nicolson scheme within a implicit scheme framework. It is a two-step procedure. So, in the first step one can do the Backward-Euler formulation. So, to use implicitly find the value. So, this and the second step, the value at time step t plus delta t can be found. So, at the first step it is the backward Euler which will get you to find rho phi t from rho c phi c t plus delta t by V c L phi c t equals to t minus delta t. Now, the second step, find the value at t plus delta t, like rho c phi c t plus delta t minus rho c phi c t divided by del t V c minus L phi c t, which will get you that rho c phi c t minus rho c phi c t minus delta t by delta t V c. So, that is rho c phi c t plus delta t equals to 2 rho c phi c t minus rho c phi c t minus delta t. So, in this calculation, one thing which is assumed as that delta t is divided into two equal steps, which is delta t local is delta t by 2. Now, one can note here is that the Crank-Nicolson scheme is second order accurate scheme. So, it is an also still it is an explicit scheme, also it is an explicit scheme which has some stability criteria or condition based on CFL like expression. So, this also has the limit of the choosing delta t, like the backward Euler or forward Euler, they are very much restrictive using our CFL criteria. Similarly, Crank-Nicolson also has certain restriction using CFL like criteria. But one thing which one can note here, since you achieve this calculation in two equal steps, so which is essentially provides slightly better stable system compared to backward Euler or forward Euler. So, this is a, and top of that it is a second order accurate scheme. So, one can note here that the Crank-Nicolson is a better option compared to forward or backward Euler, and it provides higher order accuracy even in the temporal discretization and also stable, and we will look at other scheme in the next lecture. Thank you.